Hi, good evening, everyone, and thanks for joining. Let me also thank the organizer for giving me the opportunity to present my work here. This work is available in this archive number. You can take a look at it. This work is being done in collaboration with Akash Misra, who was a postdoc here, and Shudipta Sarkar, who is a faculty at IIT Gandhinagar. You can probably take a look at this paper. Let me start with the brief motivation of this work. We all know that our current understanding of gravitational physics is based on Einstein's theory of general relativity. And it is an extraordinarily successful theory in the sense it describes a plethora of gravitational observation quite successfully, like all the classical tests which we know in, let's say, in our MSCs or so. Like light deflection around sun, perihelion precession of Mercury, etc. Then there are some recent modern tests involving gravitational wave observations and black hole shadow imaging. In this particular talk, we will focus mostly on gravitational wave because this gives us opportunity to probe GR in a more dynamical and strong field regime. Because as you know that when two mergers collide, we are basically probing a vast amount of length scale, starting from a very far away and then going towards the high energy regime. But with this increasing list of GW tests, let's not forget about the basic ones, and that's why I put this slide where I will talk on these three important tests, which you can consider as basic tests of GR. So given any waveform, you can consider this kind of test. The first test is the PPN test. It is called parameterized post-Newtonian test, which only, so this is an in-spiral only test. Okay, where the objects are too far away and radiating GWs and getting closer together. So in this test, what you want to do is that whether the in-spiral signal that you are obtaining from, let's say, LVK measurement, whether that is consistent with GW prediction, GR prediction. Then you have the test of which is known as the Q&M test, where you consider the ring down part of the signal and ask the same question whether the ring down part is consistent with the GR prediction. Then there is a little more, I will say, complicated test than these two, which is known as this IMR consistency test, where you chop the signal into two parts. One, let's say you chop it here. So that means that one part which is low frequency and other part is comparatively high frequency. And then you use GR fitting formula from this part to predict the final mass and spin of the object. And from this part, you can directly calculate the final mass and spin, and then see whether at the end they are consistent with each other. Okay, if GR is correct, they should be, and that is another test. But as I said, there are over the years people have proposed other tests also. So because there are many tests, so let's have a systematic understanding of various tests. Where in this figure I have plotted various motivation behind various tests, right? Here the three axes are axis of which I am calling it axis of ignorance, that is dynamics, phenomenology, and kinematics. So these are the three independent way you can introduce new physics on top of GR. Okay. So in the dynamics, what it means is that you change your GR field equation by adding higher curvature terms or extra field degrees of freedom. And there you can use like PPN and ring down test to constrain them. Or you can constrain whether your spacetime metric is Kerr metric or it is deviated from there. So there are ways to constrain them, and the methodology is usually known as post-Kerr paradigm. And there you can also constrain PPN and no-hair test. Similarly, but these two tests, they always assume the spacetime metric, which is describing the black hole or any other object, they are basically Kerr-like in the sense the symmetries of the spacetime are same as Kerr. But in a non-isolated system where the black hole have some external medium or some tidal effects, there could be some deviation from symmetry as well. So one should consider the other direction, which is called kinematical test. And in this way, you are basically probing whether your spacetime has the same symmetries as Kerr or not. And this is not a very well explored direction, but in this talk, we will discuss more about them, and the work is about that. But before going there, let me recap some of the Kerr symmetries and basic properties, because that's what the talk is on. The Kerr has three basic symmetries: the stationarity and axis symmetry and circularity. Stationarity means the spacetime is invariant under time translation. Axis symmetry means the spacetime is invariant under rotation about an axis. And circularity means if you flip T phi to minus T minus phi, all the physical observables should remain same. Okay, so this is the three symmetries of Kerr metric. But this is a symmetry only when you consider isolated spacetimes. Okay, but in most of the astrophysical scenarios, the spacetimes are not isolated, and there could be deviation from these symmetries. Okay, and in this talk, we'll let's consider non-circular deviation. Okay, that is when the metric. Okay, so remember the Kerr metric has up to this part, which is written in black. But if you have extra term like TR, R phi, etc., that will give rise to non-circularity in the space-time. And we want to constrain such effects using GW observations. And testing them are very useful because circularity implies various theoretical and observational consequences like horizon rigidity and validity of black hole thermodynamics, etc. So you are indirectly constraining deviation from these theorems or these results also. But how to test it? We can take hint from our knowledge from classical mechanics or quantum mechanics, where we know that symmetries in the space-time always gives rise to degeneracies of observables. And similarly, the same thing happens here. The circularity gives rise to twin modes in QNM equation. If you look at the black hole perturbation equation, it does not matter what V of L is. Okay. What is the functional form of VL is that there are two sets of QNM modes for a fixed value of M. For example, if you take 220 or 2 minus 20, for 220, there will be a set of mode which is one set is prograding, another set is retrograding with respect to the black hole. And then for even for 2 minus 20, one set is prograding, one set is retrograding. So this is very clear because the spacetime is rotating, there are two sense of rotation. But if you now further assume circularity, what you can show, the prograde mode here and the retrograde mode here, they are degenerate, okay, like this. And similar, and the retrograde mode here is related to prograde mode here also, okay. So what it means is that if you break circularity, these degeneracies will be broken, and that gives us an observable to constrain from GW, right? So this is the new waveform that I will consider. Remember, in the Kerr waveform, you have this parameter omega 220 prime and tau 220 prime to be same as Kerr. So that is delta omega 1 and delta tau 1. These deviations parameter are 0. But in this space-time, there will be deviations because the degeneracy is no longer there. So our model is that we will consider omega 220 and tau 220 same as the Kerr black hole, but we will consider delta omega 1 and delta tau 1 two independent parameter to be constrained from observation. Here we will only, so this is for the fundamental mode only, but you can consider fundamental mode plus other overtone. Another crucial point is that here is that this test is not same as no-hair test, because in the no-hair test you usually assume all the symmetries of Kerr black hole are true. Okay, so this is not a no-hair test also. This is a new independent test. So here are the some posteriors. So these are the uniform priors that I have given on the all the parameters of the theory or the model. And if you take only the fundamental mode, and so this is the, let's say, marginalized posterior distribution over the parameter delta omega 1 and delta tau 1. As you can see, so there are two things to notice here. First of all, this black line represents the null hypothesis, and which is consistent with in a 90% credible interval. And the base factor is about 2.1 or so. So what it means is that data favors the Kerr paradigm. Okay, in Jeffreys criteria, this is not a very big number, but because it is greater than 1, you can say that data prefers the Kerr paradigm. Similarly, if you consider 220 plus 221, you also get a base factor of this sort. Here you can also see, here you can also see the, so these black lines are consistent within 90% credible interval. Okay. Okay, so here are some take-home messages that this test of space-time symmetry using gravitational waves, this is an alternative test which are basically proposed in our paper, which is a new alternative test. It is not well considered in literature, but I think there are a lot of potential in this direction. First of all, and second is that if you consider future detectors, because there will be improved sensitivity and ring-down SNR will also increase. So the SNR we have considered so far is of the order of 10 or okay, of that order. But if you consider, let's say, ET and this kind of detector, there the ring-down SNR will be quite high, and you should be able to constrain this deviation parameter much more better. Okay. Then You can also consider a particular theory and then get a non-circular solution. There is actually one theory which is called the scalar coupled theory. And in that theory, we know of a non-circular space-time, and there you can use these constraint, right? These constant to see that how the parameters of that particular theory or the coupling constant can be constant. Okay. And finally, okay, so this is an open challenge. Is that a lot of people work here on shadow imaging. So I think there is an also potential direction if you use this kind of technology for shadow imaging also, because even in the shadow, if the space-time has certain symmetry, in the shadow there must be some observable which is linked to that. For example, if the space-time has Z2 symmetry, what it means is that the north and south part of the shadow look the same about the equatorial plane. So similarly, this circularity also should mean something to the shadow imaging. And this is also an open direction which can be seen in future. Okay, thanks. I will take questions.
Questions?
Yeah, so in GR, are there non-circular stationary solutions? No, right?
No, in vacuum GR, there is a theorem by Wald which says the stationary axisymmetric solution must be circular. Okay, and it has to be asymptotically flat also. But if it is non-vacuum, there is no such theorem. But if you consider, let's say, other non-isolated system, okay, which is, of course, let's say there is tidal effects, etc., or there are some, let's say, new physics, because, let's say, some higher curvature terms you have to take into account, there is no such theorem. And there are actually exact solution of modified gravity where non-circularity can exist.
So the base factor that you showed,
yes,
there, the null hypothesis is that you have GR and
car, basically.
black hole, and it's isolated and asymptotically flat. And
correct.
What is the other assumption? Is it that
the other assumption is that whatever is the new solution I am doing, so that is the non-circular solution. So the main assumption is that it is non-circular. So because it is non-circular,
for example, in code, how do you implement that? You define a metric, a very general metric.
You don't have to do that. What you can do is that you can, like the no-hair test of Tucholsky, right? So what you can do is that if phenomenologically include a term delta omega 1 and delta tau 1 in the waveform model itself. Okay. And then you constrain it, because these kind of parameters, they cannot arise from any other, let's say, hairy solution. Because in hairy solution, usually assume all the symmetries of the Kerr paradigm are.
In that sense, it's more or less like whatever people do for parameterized TGR, for example.
It is similar, but it is, I will say, it is new, because in TGR, what they do is that they put the deviation parameter in the mode-to-mode basis, like fundamental mode. Let's say you put the extra parameter in the overtone itself, not in the fundamental mode. So there is a hairy modifications kind of thing, but it is in the symmetry kind of.
So, okay, if you for some, from some signal, something you say that you get some non-circular base factor, for example.
Yeah.
How would you interpret that? Do you interpret that there is a second object, or
as I said, there can be multiple interpretation of that.
But first of all, you just
first of all, it could be that there is some non-trivial environmental effect. That could be one of the reason. So, like, let's say third body giving some tidal field on the object. Secondly, is that you are missing some physics in the near horizon regime. Like, you work on these kind of things, like if the horizon reflectivity, if the horizon near horizon surface has certain reflectivity, that kind of object can also have this kind of because this theorem is only true for isolated object. Whatever else is not happening. Yeah.
Okay, thanks. We can talk about.
Yeah, we can talk about it. Yeah, you have it. Yeah.
Someone was asking, like, I mean, if you have multiple such, cause for this change that you're showing from Kerr.
Correct.
I mean, like, it could be just Einstein GR, but not Kerr.
Yes.
But it could have also been that there's some higher derivative Kerr theory and so on. How would you delineate between what is giving?
Okay, so as of now, the source, we are remaining agnostic about the source of this deviation. We are just saying that whether you can say at all that whether there is a deviation. But of course, it is like in the same vein as PPN test. Right? In the parameterized post-Newtonian test, what you do is that in the phasing formula, you add certain deviation term, you constant them, but you don't necessarily speak about from where they are coming from. Here, we are doing the similar kind of analysis here. But of course, if you fix something, let's say you say that, okay, this deviation is only coming from due to some tidal effect, or some missing physics at the horizon, which you can give explicitly in the as an input. There you can constant the parameter which is coming there. But in that sense, it is agnostic of that. Okay. Thanks.
Is there any more question? Okay, then let's thank Raj.